Hello, this is Dr. Muhammad, and this is Design of Steel Structures according to AISC Compression Members. This is part number 5, and in today's video I'm going to talk about mainly about 3 main points. I'm going to give some examples on using the alignment charts that we have already explained in the last video, and after that I'm going to talk about the effective length of inelastic columns, and I'm going to give a couple of examples on it. And after that, I'm going to talk about the torsional and flexural torsional buckling mode failures of columns. And I'm going to wrap up with the different types of mode failures of column. Okay, so let's go now to the next slide and start with examples on the alignment charts. Okay, so we have this example for now. We have a rigid frame that is, as you can see here, this is the rigid frame, and in this rigid frame we are going to like investigate the element or the column AB, the portion of the column which is AB, and in this frame it is unbraced frame, so this frame is considered to be like moment frame, or the sway is permitted. Each member is oriented so that the web is in plane of the frame. So I mean that the web is going to be in the plane of the frame, means that the strong axis in the plane of the frame. So they are like making something like this, for example. If we're going to take a cross section here, okay, this is the meaning of in the plane of the frame. So the web is in the plane of the frame. Determine the effective length factor Kx for columns AB and BC. So we want to check the effective length factor Kx for AB and BC. Everything is given for this frame. As you can see, we have the distances here, or the spans, 20 feet each here, and this is 18. And for the height we have 15, 12, and 12. So, and also for the cross sections of the beams or girders framing into point A, they are known for us, and also the girders cross sections framing into point B, they are known. All of them, they are wide flanges, and also the columns above and below point A, and the same for point B. Everything is known for us. Okay, now let's start with column AB and start with the point A, joint A. So for joint A, we are going to calculate G, which is the ratio between I column over L column, the summation of I column over L column, over the summation of I girder over L girder. So here, if you are going to check it, you're going to find that I column, we're talking about all the columns framing into this point, okay, point A. So we have wide flange 12 by 96, and here wide flange 12 by 120. So we can obtain these I, or the inertia, from the table, from the dimensions and properties table. Easy for us to obtain it. LC here is going to be 12 feet, as you can see. 12 here, 12 and 12 for the columns. For the beams, also these inertias we can obtain it from the tables, and we have the length to be 20 and 18. So we have 20 and 18, which is this girder and this one. For joint B, we are going to follow the same procedure. We know the inertias from the properties table, and then we have L column, it is going to be 12 and 15. We have here, this is 12 and 15 because we're talking about point B. And IG over LG, it is going to be already calculated before here in the point G. It is going to be the same. We're talking about the girders, because the girder here and here, they are the same. And to the left, they are the same as well. So we are having the same number, okay, so it is repeated here. With the ratio, we can find that the GB is 0.95 and GA it is 0.94, okay. Then the next step is going to the alignment chart for side sway like uninhibited. Okay, we call this is unbraced or sway permitted. So this is based on AISC figure C-C2.4 with GA 0.94 and GB 0.95. So we can find Kx equal to 1.3. Let's have this. So we are going to go to the alignment chart. As we said, we have side sway prevented here and side sway not prevented here. So we have two types. We are going to use this one. We are in the case of unbraced. Take care, we are in unbraced case. So this means that we are going to GA. So this is the point A and this is point B. So for GA we have 0.95, so almost here, and then for GB it is 10, so we're here. So if you are going to make a line, okay, oh sorry for this. So if we're going to make a line from here to here, for example, I'm very sorry, I cannot control the straightness of the line because it's a little bit difficult. So anyway, you're going to find that the point that is intersects is going to be here. Okay, so we are going to have Kx 1.85 almost here, as I said. Okay, so this is 1.85. Okay, for our column. Okay, for joint A and joint B. From the alignment chart, I think that there is, okay, let me check something here. Okay, I think that there is a mistake. I was talking about joint or the element BC here. Okay, so actually we should use 0.94 and 0.95. Okay, this is supposedly to be the two that we are going to use, 0.94 and 0.95, and Kx for this member is going to be 1.3. Let's go here and see. So 0.9 here, 0.9 as we said, 0.95 and 0.94 and 0.95. So 0.94 and 0.95. So we're going to have a straight line almost here. So we're going to find this value as 1.3, right? This is 1.3. Yes, that's right. So we are here almost. So we are here. So it is 1.3. This is for member AB. Okay, this is for member or column AB. We are going to repeat the same, okay, obtaining the same G for point B and C. Point B already we have obtained it before. So we know it's 0.95, and point C, it is hinged. So this means that our point, this point C, we're going to have G for it to be 10. Okay, I'm sorry for this. For column BC, for joint P as before, it is going to be 0.95 because we have calculated this. Okay, and for point C, it is supposedly to be 10. Okay, so GC supposedly to be 10. Then we are going to enter the alignment chart with G. Yes, I think there is a mistake here in the textbook. I think this is supposedly to be GB, and this is supposedly to be GC. Okay. So because we are talking about column BC, so you're going to find this in the textbook, so maybe it's a kind of mistake here. So we're going to use GB 0.95 as before, and GC going to be 10. Okay, so it is 0.95 here, and we have 10 here. If you are going to make a straight line, sorry for this, as I said, I cannot control the straightness of the line. So here anyway, it is going to be like 1.85. Is going to be 1.85. Okay, remember that we are using side sway not prevented or side sway permitted. So this means that our K is going to be larger than 1. Okay, so only take care of this mistake in the textbook. Okay, so now this is the example that we have worked up till now. This is a side sway permitted case. Okay. Let's go to another example and check it. Also, it is going to be an example similar to the previous one where that we do not have any bracings here. So we're going to use the alignment charts and we are going to obtain the values, or at least we are going to have the values of GA and GB for the elements. Okay. So first of all, whenever that we have a frame like this, we can make a table which is going to be easier for us if we're going to calculate GA and G or the G of the end of the columns for all columns in the structure. Then we can make it in a table like this. We can give numbers for the columns 1, 2, 3, 4, like put the member numbers here, and including the girders 5 and 6. So it is 5 and 6, these 5 and 6 for girders. And then we have, this is actually maybe part of something or part of calculation B column. This is the not needed here. We do not need any forces here to be calculated. And we are having the Young's modulus that is given for us. I, we need to calculate it, or we can obtain it from the tables. L is giving for us for each element or each member, and then we are going to calculate IL, whether it is for columns or for girders. Okay, so we can put it in this easy way. This is actually this example to like train you to use whenever that you are going to use a frame with many columns here and there, and you need to make like hand calculations or calculation sheet by your hand, then it's better to use this kind of beam. Then you are going to find that we have columns 1 and 2. They are pretty the same, like similar. We have like the bottom is going to be hinged, means that GA is going to be like 10. And then 0.3 and 0.4, they are the same, right? They are the same. So we're going to calculate it only once. So for columns 1 and 2, this is why we put it under one title, we can make it easy for us. Like the bottom is going to be, GA is going to be 10 because pen connection is there in the foundation. And in the top we have 3 and 4. They are having the same I column and girders, because if you look to member 2, 1 and 3 and 2 and 4, they are going to be, if you look, you are going to find that they are the same, 1 and 3. So this is 1 and 3. Sorry, they are not the same. This is 63. Okay, 63 like 0.4, and this is going to be 75.4. Okay, 1 and 3. Yes, I mean that not they are not the same, but 1 and 3 they are like equal to 2 and 4. 2 and 4 also 63.4 and 75.4. This means that member 1 and 3, they I and L like equivalent to member 2 and 4. So we're going to calculate it only once. So we're going to say I column over L column, which is 75, okay, 0.4 plus 63.4, which is I column, okay, for like column 1, for example, and this is for column 3, and then over I girder over L girder. Okay, I girder over L girder, which is going to be 82.9, which is given here for us. Okay, this is for girder 5. Girder 5 is different than girder 6. So this can be calculated like 1.67, and we have GA to be 10. Okay, then we can from GA and G be going to the alignment charts, and then we can obtain the value of K. Okay, you can do it as an assignment for you. And for column 3 and 4, it is the same also. Column 3 and 4, which is this column and this one. Let's erase here everything. So we have column 3, and column 4. Also, the top is girder 6, and the bottom is going to be girder 5 for both of them, and the vertical elements are going to be the column itself 4 and column 2 here, and column 3 and column 1 here. So we can calculate it also under one title. They are going to be the same, column 3 and 4. So we have GA for it is going to be 70 for I column over L column, 75.4 plus 63.3. Okay, which is like this is the columns, column like 2 and 4, 2 and 4, 2 and 4. Or for this column, which is going to be column 3 and 1. So 3 and 1. They are the same. I mean that the summation is going to be the same. So GA is known, GB is going to be the same because both of them, they have the girder 6 here, right? Girder 6. And in the same time, both of them, they have column 3 and 4. So we are having 75.4 for the columns, column 3 and 4, 3 and 4, they are the same, 75.4 and 75.4. And for the column, it is 26, okay, because it is girder number 6, which is 26.5. Okay, so now we have GA and GB. You can go to the alignment chart and get the value for K. It's an assignment. Okay, so now I think that it's pretty easy for us and simple that to use the alignment charts. Okay, you're going to see whether that your frame is side sway prevented or side sway not prevented according to the alignment chart, and using the values of GA and GB you can get the value of K. Okay, now let's talk about the effective length of inelastic columns. Okay, what is inelastic columns? The first question is, well, what is the inelastic columns? We were talking about alignment charts for columns in general. Why now the word inelastic appeared? Okay, simply because this alignment chart that we were talking about, they have been derived based on elastic columns. So elastic column theory. Okay, do you remember that we said that if we have like we have two parts here, part at the proportional limit. We have here, this is going to be like elastic, okay, and here is going to be inelastic, right? So this is the part, this alignment chart works for. However, this part, which is the inelastic, no, we need to calculate or derive another alignment chart. So the point is, we need to understand first why we need to study the effective length of inelastic columns. Okay, first of all, the alignment chart method was developed for elastic columns. So it was for this part here. Okay, this is for elastic part. However, for the inelastic part, which is this part here, we need to for inelastic part we need to like the alignment chart will provide larger value for the effective length. This means that we're going to be like over designing our columns. Okay, over designing, because there are some part of the column is going to fail by yielding, not by buckling. So we are having some part of the column is going to serve for resistance. So we are supposedly to reduce the effective length, or the effective length factor in this case is going to be larger if we use the elastic alignment charts. So this leads to longer columns length and to conservative results for column strengths. That's right, we're going to use a very conservative, it's not economic for us. So the effective length factor K for inelastic columns can be approximated as follows. We can approximate it in a way that is going to be easy for us to calculate. The idea is that we are going to use factor called stiffness reduction factor. this stiffness reduction factor is going to be used or going to multiply the effective length factor in order to reduce it. So that's the idea, that we're going to use something called tau A, for example, and we are going to multiply it by our K, which is the elastic effective length factor, and then that's it. This is how we can like overcome this problem for us. Okay. So let's go now and understand what is the background or rationale behind this. Actually, for G inelastic, okay, which is the ratio between the summation of inertia of columns and beams, here for the column, the point is we are using ET because we are in the inelastic range, right? So this ET is going to be different than E, which is the Young's modulus of the steel that is going to be used for eye girder, right? Because again, we are in the elastic range, means that the if you remember that this is the point, if we are going to have the stress strain curve, we are in the point here. Okay, we are here, a point that is differentiating between the elastic part and inelastic part. Here we are going to use E tangential. However, here we are using E only, right? So G inelastic needs to take into consideration the tangential Young's modulus. So if we say that everything is going to be the same, then we are going, if we say that this is going to be the ratio for the elastic case, right? This is for the elastic case as we have done before. And then ET over E, we do not know it. It's something new for us. We do not know because we do not know ET. So we're going to give this a designation like this, tau alpha times G elastic. Okay, so now G inelastic is going to equal to tau alpha times G elastic. That's how we are going to use. Okay, then we're going to try to find a way to make a relation here. If you remember, we have ET over E times G elastic. Look to this ET over E. We are going to multiply the numerator by pi squared over L over R squared, and the numerator with the same value, pi squared E, pi squared over L over R squared. Then this numerator is going to be what? Exactly the critical buckling strength in the inelastic range, because we use ET here, right? And the numerator, it is going to be the critical buckling length for the elastic case, because we use E, right? So the ratio between the two actually is going to be what? ET over E, right? Which is going to be tau alpha. So this means that tau alpha, let's erase everything here and go back. So G inelastic equal to tau alpha times G elastic. So now we want to know how to get this T or tau alpha. Okay, this tau alpha is going to be simply, it is going to be, according to what we have derived here, it is going to be the ratio between the critical buckling in inelastic range over the critical buckling strength in the elastic range. If we could know these two, we can obtain tau alpha, and from tau alpha we can multiply by G elastic, and then we can obtain the G inelastic. You understand? This is the story of this part. This is the story of the tau alpha and how to obtain G inelastic from G elastic. So the point is, our intermediate step is how to calculate the FCR inelastic and FCR elastic. We want to calculate them. If we could calculate, then everything is going to work for us. Okay, now let's go and see how LRFD or how ASIC was making this approximation to work. Okay, so ASIC uses an approximation for the inelastic portion of the column strength curve. Do you remember? So equation 4.13, okay, which is this equation, okay, this equation 4.13, okay, is an approximation when AISC equation E3-2 and E3-3. Do you remember these equations? We have explained them in the previous videos. Are used for FCR, and that's right. We can approximate FCR, the critical buckling strength, by compressive strength. That's the assumption that we're going to work with. FCR, we are going to equate it with compressive strength. So what is the meaning of this? For LRFD, we're going to assume that FCR is going to equal P ultimate, which is the load that we are going to apply on the element, over phi C times area gross. And if we're talking about ASD, it is going to be omega C times the actual load or the applied load over area gross. Okay, again, this is the trick that we are going to use. We are going to say FCR is our applied load. It is our applied load or ultimate load if we are talking about LRFD. Then in the elastic range, we are going to assume that FCR inelastic, okay, is approximately, this is an approximation, for LRFD, if we're talking about LRFD, P ultimate over phi C area gross, okay, equals to 0.658 raised to the power F yield over Fe, okay, times F yield. So now we know P ultimate, this is the required ultimate strength. Phi C, we know it, okay, it is the resistance factor, reduction resistance, or the resistance factor, okay, 0.9 for example. Area gross, we know it for our cross section. F yield, it is known. F yield here in the power is known. Now the only one that is we do not know is Fe. Everything is known in this equation, then we can get Fe. Okay. Similar, this is if we're talking about LRFD. If we're going to talk about ASD, then we're going to use the same approach. Omega C is known for us. PA, it is going to be the actual load. AG, it is the area gross, we know it. Everything here is known in the right hand side except for exactly Fe. Fe is not known for us, so we can obtain it. So we can obtain Fe. So after obtaining Fe, what we are going to do, then we're going to get FCR elastic. FCR elastic equals to 0.877 times Fe, which is already obtained from the previous step. Then this is FCR elastic. We are having now the two main numbers or values needed for tau, right? Remember that tau alpha equals to exactly G inelastic over G elastic, which equals to, as we said before, T alpha or T A. It is equal to FCR inelastic over FCR elastic, right? So from here, let's go to the next step. We are going to know what is the main steps that we should follow in order to get this tau alpha. First of all, approximate the inelastic buckling strength, okay, by the compression stress. That's the first step. So we're going to say FCR inelastic equals to P ultimate, if we're talking about LRFD, of course, over phi C times area gross. Then from this, we are going to get, after that, we're going to get Fe by saying FCR equals to P ultimate over phi C over area gross times this approximation from, according to AISC. This is the only unknown here is Fe. Then we are going to obtain Fe from here. Okay. Then compute FCR in elastic using the Fe obtained from here. Then FCR elastic is going to be 0.877 Fe. Then our tau alpha or tau A, it is going to be FCR inelastic, that already we have assumed from the beginning based on the required strength, over FCR elastic, which is already calculated. Okay. Then at the end, G inelastic is going to equal tau alpha times G elastic. Okay. Do you understand this step? If these steps, if you do not understand it, please stop the video and look again to this like this flow or these steps, you're going to find that they are coherent. The only thing that we have assumed in the beginning, that FCR inelastic is going to equal to the compressive stress. That's it. Then we go through the remaining steps. Okay. Now this tau alpha, actually it is provided in the manual. So it is provided for us. If you go to table 4-21, so please stop the video now and go and bring your manual and check this table, table 421. We have tables from 4-1 to 420. This is the tables related to the column, and then table 4-22 also related to the columns, but 4-21 it is related to the stiffness. We call it the stiffness reduction factor, tau alpha or tau A. And this is the meaning of tau alpha. It is the ratio of the tangent modulus E tangential or ET to the elastic modulus E, as we have explained many times before. Okay, this is what tau alpha is all about. Okay, E tangential over E elastic, or FCR inelastic over FCR elastic. Okay. Okay, now this is the table that you can find in the manual, table 4-21. This is only one, this is the table here. It's one page table, as you can see, and it is given ASD and LRFD based on PA over area gross, or P ultimate over area gross if we're talking about LRFD. And F field, it is in KSI and given for 35, 36, 42, 46, and 50. Okay, that's it. This is what they are providing actually. Okay, and then you're going to find this hyphens here or dashes. This indicates stiffness reduction factor is not applicable because the required strength exceeds the available strength for KL over R. Okay. Okay. So this is the case for us here, and this is the table that you can find that is provided for ASD and LRFD. The values are provided, as you can see. That not all the values are provided actually. I mean that this is because all of them, they are, as I said, this hyphen indicates due to values that is not available here. So, and this is the like PA over area gross or P ultimate over area gross available, and you can get from here the tau alpha directly. Okay. Okay, now let's have an example and see what we are going to use. How can we use what we have learned up till now? Okay, so here it is compute the stiffness reduction factor tau alpha for an axial compressive stress of 25 KSI. So this is compressive stress given. Okay, axial compressive stress. So we're talking about like this is P ultimate here, okay, over the area gross. It is given for us, which is 25 KSI, and this is the first thing here. P ultimate over area gross. It is 25 KSI, and F field, it is 50 KSI. This is given for us also. So we have 25 and we have F field 50. Okay, first of all, we are going to have FCR inelastic. We're going to calculate it by ourselves. So it is going to be P ultimate over area gross, which is given for us 25. And we are going to add this phi c, which is 0.9. So it is going to be 25 over 0.9. It gives us 27.78. Okay. Then we are going to equate this compressive FCR inelastic with the compressive strength. This is the compressive strength here. We are going to equate it with this equation that is provided by AISC. We have F field, it is 50, known here, known here. Then we can obtain FE only. Okay, so from this equation we can obtain FE to be 35.61 KSI. Based on that, so after like if we like substitute with F field 50 and 50 here, then FE only, the only unknown, we can obtain FE 35.61. Then FCR elastic, it is elastic, not inelastic. I think this is a mistake in the textbook. So this is the elastic one. It is going to be 0.877 F yield. So it is going to be, FE, which is already we have explained or we have obtained before. Okay, so it is going to be 0.877, okay, times 35.61, which gives to us 31.23 KSI. So the stiffness reduction factor in this case, it is going to be the ratio between FCR inelastic over FCR elastic. This is the ratio between the two. So FCR inelastic over FCR elastic. This is tau alpha. 27 over 31 and gives us 0.89. What is the meaning of 0.89? Means that we are the stiffness reduction factor that is going to be used to reduce G elastic. We are going to multiply it by 0.89. This means that we are going to reduce by almost 11%. Our inelastic column is going to have reduction in stiffness by 11%. Okay, so this is the very simple example that we can use and that we can see, and we use our calculation. Okay, so what about that if we are going to use the table, for example? So let's have another example that is a little bit longer, and we are going to see how we can see or how we can use the tables. Okay, so let's read this example together. A rigid unbrazed, so this is number one, something key word here, unbrazed frame. This means that if we're going to use the alignment chart, we are going to use the case of sway permitted. It's shown in this figure, as you can see. This is the figure. Everything is given for us. It is the span is given and the heights are given. Even the points that we are going to consider as the end of the column that is under consideration. Okay, it is A and B given for us. The cross section is given, so everything is clear and given for us. All members are oriented so that bending is about the strong axis. So bending always in the strong axis. So it seems that all the members like oriented in this way. For example, if we like take a cross section here, it is going to be in this way. Lateral support is provided at each joint by simply connected bracing in the direction perpendicular to the frame. So this means that perpendicular to the frame, it is braced. All the points are braced. Why we want this, or why it is needed to be given here? Because this is giving to us a piece of information and telling us that out of plane, which is normal to this screen, out of plane buckling length of the columns is going to be the same as it is. So the effective length factor is going to be exactly 1. It is out of plane, means that perpendicular to the white page. But in plane, buckling length is going to be calculated, okay? Because it is sway permitted frame. Okay. Determine the effective length factors with respect to each axis for member AB. So we have chosen this member, which is AB, to examine, to determine the effective length factors, okay, with respect to each axis for this member. The service dead load is 35.5 kips, and the service live load is 142 kips, and a 992 steel is used, means that our F yield is 50 KSI. Okay, now let's go to the computation of the ratios, which is G factors, and then we are going to check whether the column is elastic or inelastic. Okay, we are going to check this. So the steps of the design is going to be like this. We're going to or the steps of the solution is going to be like this. We're going to calculate G for joint A and joint B, assuming that this column or AB is going to be elastic. And then we're going to check the column whether it is elastic or inelastic column. If it's inelastic, we are going to like further calculate tau alpha based on the procedure that we have explained before, and then we're going to reduce our K that we have obtained in the case of elastic GGs. Okay, now this is the procedure. Let's go and see how we're going to do this. First of all, for joint A, we need to calculate IC over LC over IG over LG. So the summation of column inertia over the girder inertia. Everything is given. Please stop the video, go to the properties table, calculate these values by yourself in order to train yourself using the tables. Okay, so we're going to find that 171 over 12. This is the length of the columns here, 12, and the length of girders are 20 and 80. 20, that's right, and 80, like left and right. And for W14 by 22 and W14 by 22, these are the girders on the bottom. And for the top at point A, it is W12 by 14 and 12 by 14. Okay, they are going to be the same. And this is right. As you can see, they are the same here. So the ratio gives us 1.52. In a similar fashion, we're going to use this for joint B, and we are going to obtain 1.36, 1.52 and 1.36. Then we are going to the alignment chart, the alignment charts. Okay, so in the alignment charts, we are going to use the side sway not prevented. This is unbrazed column. So and we are going to use 1.52 and 1.36. 1.52 here, for example. Okay, 1.52 and 1.36. So 1.36 here almost. So we are here. I think that we are here. So we're going to find that from the alignment chart for unbrazed, we are talking about unbrazed, as we said, Kx is almost like 1.4 as we have mentioned. Kx is going to be 1.4. Based on elastic behavior. Remember that we are assuming now elastic behavior. We do not know whether the column is going to be elastic or inelastic. We have no idea. We need to check this. Now, determine whether the column behavior is elastic or inelastic. Now, this is the second step for us. Second step in our solution. So we're going to check KXL over Rx for the column. And we are going to check the limit between the elastic and inelastic column behavior. So for elastic and inelastic limit, 4.71 times the radical of E over F field. F field is given. E is 29,000 KSI. This is 113. This is the limit. And KXL over Rx, for our case, it is going to be 49.83. It is much less. So in our column, if you remember, it was something like this. This is the limit here is 113, and our case is here 49 point something. So we are in the inelastic range. So as long as KXL over Rx less than our proportional limit, this means that we are in the inelastic range. The column behavior is inelastic, and inelastic K factor can be used. Okay. Then for LRFD solution, we are going to start with, we want the compressive stress. So we are going to start with P ultimate that is given for us. This is, remember here in the example, they are giving us the service dead load, okay, and the service live load. What is the reason for this? The reason is to calculate P ultimate for the calculation of the compressive stress after that. Okay, so the P ultimate is going to be 1.2 dead plus 1.6 live, and this provides 269.8 kips. Then enter table 4-21 in part 4 of the manual. This is the tau alpha table that we have had before with compressive stress P ultimate over area gross. P ultimate is already provided here, and area gross, it is provided for us from the cross section that we have. We have the cross section W10, right, by 33. go to the properties table, and you are going to obtain this value, the area gross. The ratio is going to be 27.7. Okay, then we are going into the table, which is table 4-21, and get tau alpha. Let's go to the table. This is the table 4-21 tau alpha, and we are going to find for F yield equal to 50, and for LRFD P ultimate over area gross without the resistance factor here 27 point something. We are here, right? Then under the column LRFD for 50 KSI, we are going down here, okay, down here, until that we are going to find these two values, 0.804 to 0.835. Interpolation is going to be used here, and based on this, we're going to find our tau alpha is 0.8105 by interpolation. Then for joint A, simply we're going to multiply tau alpha by G elastic, which was 1.5 before, and for joint B, it is going to be 0.18 times 1.36, which was obtained under the elastic behavior, or this is G elastic. It gives us 1.1. Now from the alignment chart, you are going to find that our Kx is going to be 1.35 based on these two. Okay, you are going to find it. So let's go to the alignment chart. It is less now. So we are having, we are having 1.23 and 1.1. 1.23 and 1.21 here almost. So we are having something here. So as they are providing it, it is going to be 1.36. Before we have obtained the value to be 1.45. Now, after considering the inelastic behavior, it is going to be 1.35. So we reduced it from 1.4. K was 1.4 for K elastic. Now for K inelastic, it is going to be 1.35. So we have reduction of this value. Okay, because of the support conditions normal to the frame, Ky can be taken as 1. Actually, in the example, they asked us determine the effective length factor with respect to each axis. Means that normal to the frame plane and in the frame plane. So in the frame plane already we have like calculated everything here, but in the out of plane it is given for us. Lateral support is provided at each joint by simply connected bracing in the direction perpendicular to the frame. So as long as there is a bracing in this direction, which is perpendicular to the plane of the frame, then K is going to be 1 in this case. K is going to be 1. But in the plane of the frame, it is unbraced frame. So we need to go into all this story of calculations. Okay. So the last thing that I want to talk about is related to the torsional and flexural torsional buckling. Torsional and flexural torsional buckling. Okay, other types of mode failures. So when an axially loaded compression member becomes unstable, okay, overall, that is not locally unstable, I'm talking about the global failure behavior, okay, it can buckle in one of 3 ways as shown. So this is considered to be like global buckling behavior. And this global buckling behavior can be considered as, we call it as flexural buckling, one type called flexural buckling. Other type, we call it torsional buckling. And the third type, we call it flexural torsional buckling. Now let's understand what is the difference between these phenomena. Okay. First of all, global buckling based on flexural buckling means that the cross-section, the whole cross-section is going to move laterally, as you can see, with this shape, with the dashed shape here. Okay. However, in the case of the torsional buckling, so we are going to find that the shape is going to like go in this way, torsional. This is torsional buckling. It will not go outside here. It is going to revolve around the center itself. This is what we call it torsional buckling. And the third one is going to be a combination of the two. So this is what we call it flexural torsional buckling. The element is going to go translation or go laterally, as you can see here with the dashed line, and in the same time it is going to rotate. So this is three different types of global failure behavior of the column. Okay, we're going to talk in detail about each one, okay, without going into the equations, because rarely actually we can find other types of failure, especially these two failures. They are not going to be commonly encountered, especially in case of purely compression members, okay? It is special cases. I'm going to talk about them in a minute. So for global flexural buckling, as we said, we have considered this type of buckling up to now. What we have studied up till now, it is based on flexural buckling. Okay, it is a deflection caused by bending or flexure about the axis corresponding to the largest slenderness ratio. Okay, this is this one. Okay, the slender, which is we have like here, this is X and this is Y. So the flexure is going to take this global flexure around the weak axis, okay, which is going to be YY, for example. This is usually the minor principal axis, the one with the smallest radius of gyration. As we know, compression members with any type of cross-sectional configuration can fail in this way. So this is the most commonly encountered failure mode that we have. Okay. The next one is the torsional buckling. Okay. This type of failure is caused by twisting about the longitudinal axis of the member. It can occur only with doubly symmetrical cross-sections with very slender cross-sectional elements. Okay, that's the point why it is rare. Okay, standard hot rolled shapes are not susceptible to torsional buckling, but members built up from thin plates, that's the point, this is the key word here, thin plates, okay, are going to be susceptible to this failure mode. That is, fortunately, that is hot rolled shapes, which is commonly are going to be used in our case. They are not susceptible to this buckling, this torsional buckling failure mode. Okay, only thin plate, okay, elements may be and should be investigated. Okay, the circumference shape shown is particularly vulnerable to this type of buckling. This shape can be fabricated from plates as shown in the figure, or built up, maybe built up from 4 angles placed back to back. So whenever that we have something like this, like star shape, and they are made of thin plates, then you should be worried and you need to check them. But if you are taking or you are working with hot rolled shapes, then don't worry about this failure mode. The last one is the flexural torsional buckling. And this type of failure is caused by a combination of flexural buckling and torsional buckling. The members bends and twists simultaneously. This type of failure can occur only with unsymmetrical cross-sections. So remember, this is a key word here, unsymmetrical cross-sections. Both those with one axis of symmetry, such as channels, structural tees, double angle shapes, and equal leg single angles, and those with no axis of symmetry, such as unequal leg and unequal single legs. Yes. So this is in case of with unsymmetrical cross sections in general, which is also not the common case for us. Okay. So we have, again, remember the failure modes that is going to be for our compression member. We are focusing our study up till now on this one. However, the other two should be investigated in some special cases. The last thing for our today's video is the failure modes of compression member in general. So we have global buckling, which is already I have talked about 3 different types of it. And then we have local buckling, which is going to be something similar to this. This is local buckling here. And then the third one is the connection failure, which is related to the connection itself, as we can see here, for example, for this element here in reality. So we have overall buckling, like this is like flexural, for example. We have three different types of it. So this is buckling of the entire column, or we have other two types as we have explained before. And we have local buckling, which is this one. And we have connection failure, which is the failure of the connection itself. We are going to talk about connections later. Local buckling, we're going to talk about the compact and non-compact and slender elements. And buckling of the entire columns, this is already we have explained up till now, and we mentioned about the flexural buckling. Okay, thank you. This is the end of this video. I hope that you have understood everything that I've explained today. It's very important video, I guess. It gives you an exposure to the failure modes of the column or compression elements. And I hope that you have an idea of how to distinguish between the different types of failure modes and what is the different types of global flexural type or global failure modes. Before that, we were talking about the inelastic column charts. By this video, we have ended columns, compression members, I mean, and then we are going to talk later after that, we're going to talk about the next topic, which is related to beams. I hope that until then, I hope that you can stop the video, pause the video at different steps and try to like learn more by going and using your manual and trying to find more information about what I have said, whether in the textbook or in the solved examples in the manual. And I hope that this video helps you to understand more. Thank you very much and see you in the next video.